Okay, so what we're going to do is we'll have a quiz on Monday, and it'll be on making solutions. And let's take a look at this one here, a little review. So let's say on Monday, you saw this question, number A, letter A. Would you have a lot of trouble doing that? And you said, no, that's pretty easy. And what I would ask you to do probably on Monday, I'd have you do all your mathematics over here. Show me all your work over here mathematically, and then actually tell me step by step how I'd make those. Is that what we've been doing in class, sort of? Okay. So what do you think about A? Think you'd be all right on that? All right, how about B? Obviously, those two are the easiest questions I can ask you in this chapter. What about C? Would you be okay with that? Would you remember to use a volumetric flask? Okay. All right. What about this one with molality? You probably know the molarity equation by now, don't you? Yes.
Can you just explain the difference between that just real quick?
Between molarity and molality? Okay. First of all, I want you to think about molarity like this big and molality like that big. Okay. So they're not even. That's for sure. And what I would do is I go to this sheet right here. I look at the definition, and I'm sorry there are so many ways to represent concentration, but there are. And look at molarity. It's moles of solute per what? Per liters of what? Solution, right? Okay. And that's why you have to use these, because it's solution. Now look at molality, little m, moles of solute per... You know what's kind of neat? What's neat is, I think they were trying to make inroads in the mole world, but if I told you it had so many moles, that'd be so many grams, wouldn't it? So you use your balance. Remember how you did these with balances? You know, percent by mass. All I need is a balance. I don't need any special equipment, just a balance and maybe a graduated cylinder. So here they are trying to use the mole idea, but I need a balance to find grams, and then I need a balance to find kilograms of solvent, right? Well, guess what they don't need? See? I don't need that. And again, I have to tell you, it took a lot of, I'd love somebody to find that. Who first started using this? When did molarity actually start? When did the volumetric flask actually start? Isabella sent me a quick extra credit thing, and she was getting there. She actually talked about the company who makes these, and one of the companies called Pyrex, and they talked about the word Pyrex came from a company who wanted to make glass that wouldn't shatter if you heat it in the oven, and the first thing they made was a pie plate, and they called their company Pyrex. I get that? So I thought that was interesting, but it didn't answer my question about when did they start using these? Because, and go back to Carson's question, see this one, I do know how much water I have. I weigh it out, right? Grams, or change to kilograms. Here, I really don't know how much water is in there. I know how much solution there is. I don't know how much water there is. Does that answer your question about what the difference is?
Yeah.
So, it's possible you'd have to be reminded of the definition for molality, but I don't want you going home and stressing on that because I'm not going to use it very much. But yeah, it'd be nice to get that one question right. But don't go over and thinking, well, I need to know that just as well as molarity. No, for sure not. Now, the other thing we did is we got down to a little conceptual thinking here, and this is where I really need to know, are you just shaking your head or do you really understand this? What if I had, let's make up a new one, all right? Let's say you come out and the molarity of this solution here, what if the molarity of this solution comes out to be 0.5 molar? All right, let's pretend that it came out to be 0.5 molar. Here's my first question. What is the molarity of iron 3 chloride? I'm sorry, not the molarity. What is the concentration of iron 3 chloride? Raise your hand if you think you know. What is the concentration of iron 3 chloride in a 0.5 molar solution? I'll try it again. What is the concentration of iron 3 chloride in a 0.5 molar solution? Yes,
0.5 molar.
of course. 0.5 mole, that is the concentration, isn't it? Now, good job. What is the concentration of iron 3 ions in that solution? 0.5 molar. For every one of these, there's only one of those, right? Right, 1-to-1 ratio. Then what would the concentration of chloride ions be? Excellent. What is the concentration of total ions? What was it? Okay, it'd be 4 times this, it would be 2 molar. Very good. What is the concentration of 10 milliliters of this? What's the concentration of iron chloride if I give you 10 milliliters of this? Oh, some of you are sharp. What's the concentration of a planet full of this? Okay, what about 1 drop? Okay, all right. Everybody got that? All right, I didn't trick you, right? Maybe a little bit. All right, so then here's a problem on the homework, which I thought we would try. And what I'd like you to try is number, here it is, that's a good one. I think number 31 is a really good one. So if you don't mind, take about 3 minutes and see if you can work number 31 and then try to show your work. All right, and again, if you already started your homework, you can just kind of put number 31 and put it on there. I better start with a new piece of paper. Does everybody have this packet? Number 31. I'm okay if you just got in and you said, well, I don't know about this. I don't know if I can do that. That's okay. Let's find out what's stopping you. If this is working for you, you're doing something I certainly couldn't do at your age. I don't think I could even do it. Even when I was in college, I was struggling with some of this. I really did not have all the fundamentals there. And are you feeling this problem a little bit? Are you saying, ooh, I gotta get in that mole world. If I can get in that mole world, I bet I could finish this problem. All right, how we doing? I'm okay if you tell me, if you're honest with me and you said, I'm stuck, then I can help you, okay? All right, let's try it. Does your problem look something like this? It looks something like that. So I wrote out the equation. It's a double replacement reaction. Is that correct? Now, we're actually not interested in that, but I did need to have that to balance the equation. I want to make sure I balance the equation. And then I know that when you tell me, you give me volume and molarity, what does volume times molarity give you? See that? That means you're giving me the number of moles of this and you're giving me the number of moles of that. That automatically sets off an alarm and says, this is a limiting reactant problem. Notice I have 2 rows of boxes there ready for me. So it is true that this is the one time you have to change it to liters, okay? Because molarity is moles per liter, and this has got to be in liters to give you moles. So this is the one time you have to change it to liters. So I think I did it in my head. Is that correct? Is that where I get that? Is that what you got? All right, did you get this one? Okay. All right, here we go. Just like old times. I have 0.06 moles of peanut butter and matchy. Boy, if you also had 0.06 moles of bread, we could use up all the peanut butter, couldn't we? Did you bring that much? Well, then you are going to limit. So this is the limiting reactant, right? If you happen to go to college and they say limiting reagent, are you okay with that? Limiting reagent. The reagents are the reactants. Okay. All right, so if you're the limiting reactant, then everything's going to be based on you, matchy. And then, woo, like that, right? Is that what you did? Is that how you did it or not? No, you didn't? Okay, so let's try it again. I need 0.06. This is only 0.05, right? Isn't that going to limit it? Okay, so then, is this a matchy? Okay, so is that what you had? Oh, okay. You're scaring me. Okay, then how do you come up out of the mole world? Okay, the molar mass, what do you have for the molar mass of calcium sulfate? It's probably 32 plus 64 and plus 40. Is that what that is? How much is it? 1/3? 136? Okay. All right, so did you multiply that times that, and did you get it? What do you think? Well, really, honestly, do you see how this chapter does tie in with stoichiometry? Now, I need you to raise your hand and say, well, I got stuck. Wait. Tell me again, how'd you know it was limiting reactant, or tell me where you got stuck. Kyle, where'd you get stuck? How did I know that I needed to write 2 rows of boxes? How did I know that? I said last chapter, if they give you grams of both reactants or moles of both reactants, you have to use limiting reactant, don't you? So, did I do that? Sort of, didn't I? You had to know what? You had to know that molarity, and I gave you that, times volume, I gave you that. What is molarity times volume? So I will be able to calculate these moles, won't I? And I did give you so many moles of that. And so I put them in different rows, didn't I? Okay, and then I try to figure out which one's the limiting reactant. I need this much of you to use up all of me. Did you bring that much? And the asterisk says, no, I only brought 0.052. So we're going to run out of this stuff before anything else. So that's going to limit how much is going to be made. And I happen to know as I go sideways, I look at coefficients, don't I? Matchy. And then come up out of the molar world by multiplying by the molar mass, right? Yes?
So, isn't that not like the total number of moles? I mean, isn't that only the concentration, not the amount of...
Okay, careful now. Big M is concentration, but moles is not. Moles is actually a number of particles, isn't it? But well, guess what happens when you take molarity? You take the concentration times the volume. What do you get?
You get the number of moles.
Right.
Is the
And that's how the chemical world operates, is how many of these things react with how many of these, isn't it?
Yes.
It has nothing to do with concentration. Now, concentration in this case times molarity times volume will give me the number of pieces. And that's what I was getting down here. I ask you a question again.
Is 0.052 already the number of moles that you have?
Well, you know it is, because who lives underground?
That's the moles.
Like this. Again, you don't have to do that when you go to college. Ever got that? The reason I always organize my moles underneath it, because I know exactly where I'm at. I'm in the mole world. If you're not down here, you're in some other world. You might be in the concentration world, the gram world, the liter world. You see that? All right, what do you think? I'm telling you, if you can do that, you're in really, really good shape. All right, what I like to do is, what's interesting is I wrote this one year, and I had a little note card, and I lost it, but I had a little index card. And I was telling them, I said, well, there are 4 equations you're going to use a lot in this chapter. And it was like this. This one says molarity equals moles of solute per liter of solution. Now, that's an equation. There's also the definition for molarity, isn't it? Now, you'll use that quite a bit in this chapter. Number 2 is molarity times volume in liters will give you moles of solute. Now, do you understand that is this equation? You multiply both sides by liters of solution, and that is volume in liters, isn't it? Now, the third one that you're going to use a lot, it looks like this. It's called the dilution equation. It says M1 V1 equals M2 V2. Now, let me show you how this works, all right? Remember when I first, in high school, there's no way our teacher would let us make our own solutions. They just never even thought about it. He probably thought, well, you can't do it anyway. I go to college, guess what? They must have thought I can't do it, because they already made it for me. So when I started teaching, about 46 years ago, whatever it was, we had a chemistry teacher. He'd been there for like 30 years, and I needed some solutions. Hey, can you make these? Oh, I'll make those for you. Okay. So I did that for a few years. And I thought, when I actually started teaching chemistry, I thought, wow, I was teaching how to do it. I was teaching mathematics, and I thought, how come I can't make my own solutions? So I started doing it, and I did that for a long time. I still do that today. The same thing, I also do this here. I'm pretty good with the money your parents put in. I don't try to waste the money at all. I don't try to buy things I don't have to buy. But for example, I can buy these cute little bottles, 1 liter bottles that are already made up, 2.5 molar sulfuric acid. and the little bottles are cute, and they're already made up for you. And I'd have to buy about 4 or 5 of them. And they cost, a certain amount, I don't know, $25 a piece. That's a lot of money. All right, or I can buy a really big jug of 12 molar sulfuric acid. All right, and then guess what I can do? If I know how to dilute that, I can make 100, or not 100, I can make 40 of those little bottles. You see that? For about $40. Now, it saves the school hundreds of dollars, as long as I'm willing to do that. And I get it. If I was in a position where I just didn't have time to do it, I just tell the school to order it, and that's just the way it is. But, and it is dangerous. I will tell you, 12 molar sulfuric acid, that'll hurt you. That will hurt you. It will, you'll feel, you put it on your skin, it'll feel like it's on fire a little bit, and then you wash it, and guess what? It still feels like, and you wash it again. And it's still, see, what you did is you damaged the nerves. You're sending your nerves, and they're damaged. They're going, hey, that hurt me. Even if you wash it off, it still keeps hurting. Another thing is, if you get them on things like your skin, it's a dehydrating agent. Sulfuric acid will take H2Os away from anything. And since there are H2Os in your skin, it'll dehydrate it, and then a few days later, that place will turn brown or black. It's like you killed them. You killed all the cells down there. Now, the one thing I have to be most careful about is the fumes. That's the so here I am back there. I usually make my solutions back there, and so I'll wear my definitely safety goggles. And but I'm gonna show you how to dilute acids, okay? But the one thing I have to do is, if I just pour it, I'm gonna pour it into a beaker now instead of a big jug, because that's a lot easier to handle. And then I have to be careful because I don't have a special room that has what they call negative pressure. It takes all my fumes away from my face. I don't have one of those. That costs a lot of money. So here's the way I do it. Okay, so I'm doing it. I'm just blowing the fumes away from me, because if I don't, and they come like here and they get my nose, that's not good. It's not good. But anyway, let me show you how to make a dilution. And this is the mathematics, and I want you to know why that works. Why does this equation work? So let's make a little drawing here. I have this great big jug, and really it's made of glass. It's like a apple cider jug, and there you go. Now, so let's say I have 12 molar. I think I'll use hydrochloric acid today. All right, so I have 12 molar hydrochloric acid, and what I'd like to have, and I have a bunch of it. I just have a bunch of it, okay? What I really need is, how much do I need? I need 500 milliliters of, I don't want anybody to get hurt, so when you were in first year chemistry, the most dangerous acid you ever had was 2 molar. 2 molar, okay? So I'll make that. I'll make some 2 molar. All right, here's what I have, and here's what I want. I need 500 milliliters of 2 molar. Get that? So what are you going to do to concentrate acid in order to make it not so concentrated? It starts with a D. You're going to dilute it. That's why this is called the dilution equation. So here's what I'm going to do. What does M1 stand for, you think? Molarity of the first stuff. And what is the volume that you're going? How much am I going to take out of this? And you said, I don't know. You're right. I don't know yet. I'm going to have to figure that out. That's my unknown, okay? Because I have to figure this out before I make it. But when I get done, what does M2 stand for? Molarity of the second solution, right? And what is it going to be? Oh, okay. And what's the volume of the second one? What is it? Now, excellent question. Excellent question. If you want to get moles of solute, you must change it to liters. You get that? But look what happens here. What happens to the big M's? Cancel out, don't they? And so the only thing that's going to be left is what? So if I want to figure out how many milliliters to take out of here, I'm going to leave that as milliliters. I don't have to switch it in this one. The only time I have to switch it is when I do molarity times volume. You get that? If I don't have to. If I want my final answer to be in milliliters, I'm leaving it right like that. All right, everybody know how to do this, right? Do this times this, divide by that. That's how you do it. Give me the answer here. So it's this times this divided by that. Is that correct? It's this times this divided by that.
83.3.
One more time.
83.33.
83.33, and the only unit left is milliliters. Now, you may feel proud of yourself that you have figured out X. I solved for X. Oh yeah? Now go back there and make it. Now go back there and make it for me. X is 83.3. Now go make it. That's a different story, right? What am I going to do? What's step 1 going to be? What am I going to go get? Oh, I see. I think step one would probably be to go ahead and get this out, wouldn't it? Let's say go get 83.3 milliliters of what? Of what? Help me out. Yes, yes. Go get 83.3 milliliters of that really dangerous 12 molar hydrochloric acid. Go get it. And all right, so I got that. I use a graduated cylinder usually to do that. Now, number two. What are you going to do with it? I'll give you a hint. Whenever you hear the word molarity, you should be thinking about these. What am I going to get? Does that make sense? Got one of these, all right? Yes. Oh, is that too big? One? Oh, I see. I got you. Thank you. Okay. Anyway, now here's the only thing different about making one of these as I'm making something else. Most chemists will tell you, you don't just put a bunch of dry chemicals in here. You always want to put a little water in there anyway. You get that? And then let them sit in the water. Then add the rest of your water like that. Okay, now, it's especially important in acids. Now, what do I mean? Put some water in the flask. What's that all about? And I'm going to go up to 500 eventually on it, and I know I have 83. So I'm just going to maybe, put it down here. And I'll tell you what. And I still remember this. It's a long time ago. There was a little, in the chemistry room, there's a little tiny poster, little tiny poster. And I remember it even had it was a fox or something like that, because I guess they thought I'd look at an animal. And it said, be wise, that add acid to water, like you oughter. And I saw online also, I saw one that had an otter, an actually otter. And it said, add acid to water, like you oughter. Okay, now what that means is, you should add acid to water. You don't put the acid in here and pour a bunch of water on top of it, because there's a huge amount of heat will occur, and it might come right back in your face. So let's try it again. Add acid to water. All right, wait. Add acid to water, like you oughter. And you know what I mean by oughter, right? Ought to, like you ought to, oughter. Okay. All right, so I'm gonna put a little water in there, and then I'm gonna put in, then I'm gonna go ahead and pour in the 83.3 milliliters of HCl. And then what? One more step, and I'll be done. All right, fill up to the line, right? Now, when I get done, what am I holding in my hand? 500 milliliters of not 12 molar anymore, 2 molar. There it is. That's how you do it. I don't know what I was afraid of at first. Why didn't I make, I think you could do it. You could do it. There is danger. 12 molar, dangerous. But other than that, if you could handle it and just be careful, you could probably do that. But I can see where colleges, they don't want you making solutions, do they? Not really. They want to make sure they're made right. Because what if you make them wrong and then everybody else uses your solution and all their answers are messed up? Your fault. That's your fault. And everybody gets angry about that. All right, what do you think about this? Now, here's my question for you. Hard question. Why does that work? Why? This is a higher level question. It is. Why in the world would this equation work? You might as well take a guess, because it's a higher level question. I'm okay if you miss it. I'm listening.
Ratio.
Not exactly. I'm gonna say not exactly. Even though ratio is a lot of answers for me, I'm gonna say not in this case. Looking at your faces. Anybody?
Are they actually, like, are the values actually equal? I guess they.
And that's a good question. And yes, you know why I know it? Because I put equals there. When I write equals, that means this equals that. How does that work? Everybody want to take a chance? All right, Jonah.
Not sure.
What?
I'm not sure yet.
Okay. Come on, nobody? All right, can I help you a little bit? What does molarity times volume equal? So, watch this right here. I'm going to take out 83.3 milliliters of this really concentrated stuff, isn't it? Now, when I take out that 83.3 milliliters, am I not taking out a certain number of moles of HCl? Isn't that right? Am I not taking a certain number of moles of HCl? What did I do with those moles of HCl? What did I do with them? I put them here. And then I added some water that had no HCl in it. The number of moles that I took out of HCl equals what? Number of moles of HCl there. Isn't that right? That's why this equation works. Are you with me or not? Okay. So let's go to your homework, and I'm going to show you. You know what? You guys are so smart anyway. Here's my homework. I lost it. What's homework? Help. I think I buried it. Can I borrow your homework? Did I not just show you the homework? That's weird. All right, I'm sorry. I apologize. Let's go to a problem just like this. Oh, I like that. Oh, I like that. 37. Let's do 37. And when you do get tests on this eventually, you're going to say, I'll eat those for lunch. Those are my favorite kind of problems. And let's do number 37, okay? Let's do number 37. Where in the world is my homework? Oh, wait a minute. My fault. My fault. I don't want you down. That's not it. I'm looking for one that's a dilution problem. Oh, that's weird. That's weird. Wow, where are they? Huh. All right. Here, you take this back. And what I'll do, I cannot believe they're not, I know they're in there, dilution problems. Let's do one. Here it is. All right, sorry. All right, what we do, that's my fault. Let's do a dilution problem, and here it is right here. What volume of 12 molar hydrochloric acid must be used to prepare 600 milliliters of 0.3 molar HCl? Let's try that. It's actually in the study guide. So study guide on page 88, or you can just look up here, okay? What volume of 12 molar hydrochloric acid must be used to prepare 600 milliliters of 0.3 molar HCl? What do you think, Jeb? You already done? I like that. You're already done, aren't you?
How many milliliters?
It says, what volume of 12 molar hydrochloric acid is used to prepare 600 milliliters of 0.3 molar HCl? Hey, every year I do these problems. Did you know that every year I do these, some people think that this is a chemical reaction and they need to set up a balanced equation? Is this a chemical reaction here? No, it's just diluting it, isn't it? It's just diluting some stuff. All right, raise your hand if you're done. Don't say the answer, but just tell me if you're done. Okay, now raise your hand if you're not done. All right, so you probably did something like this. 600 times 0.3 divided by 12, and you got your answer in what units? That's right. Now, what if the author asks you for liters? Then you change milliliters to liters. All right. You like that? That pretty easy? All right. Like that one? All right. Now, just a minute. I'm going to ask you for your paper back there. Let's do the last one. I told you there are 4 equations that are used in this chapter. The next one is called acid-base neutralization. All right, here it is. Molarity of the acid times the volume of the acid has to equal the molarity of the base times the volume of the base. Well, that looks kind of familiar. Does that look kind of familiar? Okay, so now, if I could borrow your thing one more second. I'm sorry, I know it's here. I don't know what I said on top of it. So what I'm going to do is we're going to do number 37, and let's go ahead and do number 37 up here. It says, what volume of 0.1379 molar HCl is required to neutralize 10 milliliters of 0.2789 molar NaOH? Do you want me to make that a little bigger? All right, let's everybody go ahead and start. And I'll give you a little clue. Guess what this is right here. Guess what this number right here is. It is the what? It's the molarity of the acid. Okay? And what is this? What about the base? Volume of the base. What's this? Okay, I just gave you 3 of the 4 things you need to use this equation, right? You need 4 things for that equation, right? I just gave you 3 of the 4, didn't I? Let's try it. All right, here we go. What is the molarity of the acid times the volume of the acid has to equal the molarity of the base times the volume of the base. The molarity of the acid is 0.1379 molar. The volume of the acid, I don't know. I have to figure that out, don't I? What is the molarity of the base? 0.2789 molar times the volume of the base. Jonah's going to ask the question, and he does a good job on that. Do I need to change this to liters? Again, these are going to cancel. If you want your final answer to be in milliliters, then don't change it. Everybody get it? All right, so it's going to be this times this, divide by that. All right, if somebody will tell me what that is.
20.225.
How much?
20.225.
22 point.
No, 20.225.
All right. And did everybody else get that? All right. Is that pretty easy? All right. Can I give you one that's a little harder? Okay, there's one catch. There's one catch to this equation. And by the way, before I do it, I need to give you a little mini lesson, okay? Let me give you a 1 minute lesson. Did you know that when acids like HCl react with a base like NaOH, they always get two products? Acid-base neutralization always ends in two products. One of them is a salt. Now, it's just a coincidence. It's just a coincidence that this salt happens to be the world's most famous salt. It could have been barium chloride, okay? Now, and water. Water is the second thing, right? That? Okay. Now, this one's already balanced, isn't it? This will take you back. In the 10th grade, you learned to do these things called net ionic, and we'll do that next week. Net ionic equations. And it went like that. It went like this. This ion plus this ion reacts with this ion plus this ion to yield. And you look this on the chart and you say, oh, that's soluble. If it's soluble, if it's aqueous, then it's a bunch of sodium ions and chloride ions. They're both aqueous, and these are aqueous. And then you had water. Something like that, right? And then what you got to do, and we'll practice this next week, you got to cancel out the spectator ions. Spectator? You mean the thing on the left side that looked like exactly the same on the right? Like you didn't do anything. I started with chloride ions, I ended with chloride ions. You didn't do anything. There's no chemistry there. I started with sodium, I ended with sodium. You're spectators. So what's left? What was the only chemistry that took place here? Hydrogen ions reacted with what? And yield what? Which is neutral. Neutralization. This is the net ionic equation for neutralization. Now, here's my question. Why does this work? Why? Why does this equation work? All right, Caleb, I think you know, but you've been sitting there all period. Come on. Why does this work? Why is that? Why can I say that equals that?
Because you're finding like how many moles of hydrogen and how many on the other side, how many moles of
So what happens if the number of moles of hydrogen ions equals the number of moles of hydroxide ions?
it will be completely neutralized.
It'd be completely neutral, wouldn't it? Oh, you see how this works? This is moles of acid, but it's not, that's a little catch. It's not really moles of acid, it's moles of ions that made you the acid. You get that? Yes, no? And this is not really moles of base, it's actually moles of ions that, hydroxide ions, isn't it? That made you the base. And when they're equal, is it an acid or base now? If I have more hydrogen ions, I'm an acid. If I have more hydroxide ions, I'm a base. What if they're the same? What's that word? Neutral. That's why it's called a neutralization equation. Does that make sense? All right, I'm going to make you do a hard one, and I know you're going to think, there's no way I'm going to miss this question. 38. There you go, 38. I will give you a pat on the back if you get this one right. 38. So this equation is very similar to that, but this is an actual chemical reaction, isn't it? When you get done, check your answer. I actually put this online, but if you didn't look online, I'll give it to you anyway. Here's your answers. Check your answer, then shake your head a little bit and say, what happened? What happened? How can I miss this problem? Everything was pretty simple. You wrote that answer yet? Check your answer. And let's see if there's any aha moments here. Oh, aha. See. All right, what'd you get? The author says, sorry. The author says the answer should be, he says 183. I'll bet you didn't get 183 first time you did you? And I'll tell you why. Look up there. I agree. Look at that NaOH. For every NaOH, how many OHs do you have? 1. So whatever the molarity of the NaOH is, that's the molarity of the OH, isn't it? But look at the next thing. Not a monoprotic acid. I mean hydrogen ion. Diprotic. So if I had something that was 0.2789 mole, 0.5 molar H2SO4, what would the concentration of hydrogen ions be? Not 0.5, but what? Yeah, for every one of those, you get 2 hydrogen ions, don't you? So what's the concentration of hydrogen ions? 1. Now, if you put that in, is that what you did? You put 1 in there? You thought about it? Okay, good. All right, I'll tell you what. I think that the quiz, I don't know if it's going to have all these. It mostly would be making solutions and maybe a dilution from, okay? I think we need to revisit this before I look at this on the quiz, all right? Is it okay? We have a 3-day weekend, and I think you could do pretty well. I would just do some homework problems, really. Just do some homework problems, and don't do the ones that we haven't done yet. Don't do the ones we haven't done. What'd you think? I wish, I love it. I see you guys are making connections. You're making connections. Switch on, switch on, you know? We have nice, I have about 10 parent conferences tomorrow, but you guys get to go. It's going to be a really nice weekend. I think the weather's going to hold up, and so you guys have a nice break, okay? Thank you. Hey, good work today. Good work.